Okay, so we're in. All right, we're running. So the first quiz. So you had a. I'm just going to write it out. So you had a. This would be quiz one. So you had a voltage supply of 60, plus on top, minus on the bottom. You had a resistor up here, 5K. And I'm just going to go through the switch. I'm going to go to the 10K. And, excuse me, this is, 5K, 10K. And then this is your capacitor over here. And then this is 20 microfarads. And the thing was to write the voltage across the capacitor after the switch is closed. So basically the switch is right up here, but we don't worry about that. So basically we want to go and we want to look at this, and you can't do it with that circuit. You can do it with this circuit, okay? So you got to Theveninize. So you got to cut the circuit and then ask what the voltage is. What is this voltage right here? What is this resistance right here? And then you can do it. So if you cut the circuit right here and you ask the question, what would be the voltage across the 10K? Well, it is 10 V Thevenin is equal to 10 over 10 plus 5, which is voltage divider, times 60, or 2/3 of 60, or 40. So you come over here and you write 40. Questions about that? Everybody got that. I think just about everybody got that. Then what do you do with the rest of it? Well, now you can get it. Now you have to find the resistance here. And so you look from this point and you go back and look at the resistance and you short out and you basically look at it this way. You say, start here, you go through this resistor, you short this out, and then you go through this resistor. And these are in parallel. So it's 5K in parallel with 10K, or what? So I start here and I go backwards. So it's R1, R2 over R1 plus R2. And that's my resistance. So it's 10 times 5 over 15, or about 3.33K. Right? Yeah. So I write that up here, 3.33K. Now I've got my circuit that I want, and this is my 20 microfarads, and I can use my formula. So it's what? 40, 1 minus e to the minus t over tau. And that tau is equal to RC, which is equal to what? Say it again. It's 20 times 10 to the minus 6 times 3.33 times 10 to the third, or what? 66.6 times 10 to the minus third, something like that. Is that right?
Yeah.
Thanks. Any questions about that? So some of you, a couple of you, start rounding immediately. Don't. Please write it as close to the right number as you can. Most people say 3 significant figures. If you start rounding immediately, you've been taught sometimes to round. Don't in this class round. I'll give you something and I want something. I'll give you units. Okay? What are the units? I don't care. You'll figure them out eventually. And the units are usually milliamps or k ohms or volts. You usually are in that range. So I'll give you the units. So if you don't put units down, if you don't put the little term volts over here, I don't care. I know that's what you meant, even though you should, okay? I'm going to give you that. But on the other hand, I want 3 significant figures if possible, and I'm not going to take off. But please, as you start doing things, they stack. And if you round that to 0.7 or round that to whatever, and then you use that number and downstream, all of a sudden your numbers start to really go off. and your numbers don't jive, and we can't. I can go back and I can calculate your numbers and see if you got it close, and then I usually give you credit for it, but don't. So just please, as you do these problems, keep the significant figures as is. Okay, so that's number one. Number two, I equals C dV over dt. So 10 times 10 to the minus 6 is equal to 100 times 10 to the minus 6 dV over dt. So the slope of voltage with respect to time is the so the change in voltage, so that with respect to time. So if you said, okay, so here it is, 10 times 10 to the minus 6 is equal to 100 times 10 to the minus 6. The change in voltage, dV, over the change in time, which is 8 seconds. And the answer is 0.8 volts. So you write the slope and then 0.8 volts. Minus 0.8, because it's going down, okay? So the current is going from the minus side, it's a minus. I took off 1 if you said minus. I usually don't take off for that, but I thought, well, first time around, I want you to get it, so that was why I did that. Any questions on that quiz? Okay. I'll try to do a quiz a week if possible. Sometimes I won't. You'll be thankful when you don't have one, but something for you to do over the weekend and think about it and try to study the stuff. And obviously, I want you studying. I want you being aware of what's coming next, and that's just part of this course. Is you know, it's like anything else. The more you put into it, the better you get, and that's all I can say. You have to study this stuff. You can't just put it under your pillow and sleep on it and think you're going to get it. It doesn't work. It does not work. Okay, chapter 2. Now we get into the part, I call it the heart of the course, but it's pretty straightforward. So again, once you get this idea, the next few chapters can be kind of, I hate to use the word boring, but once you get this down, this process, you say, well, this is the same as it was in resistive circuits, and it is. Okay, so again, I don't want to disappoint you with this course, but this course is a course in something that has been classically done, that you always have to think about how to do this, and there are some very practical, and we're going to talk about them, reasons why you have to do this and understand this, but daggone it, once you've got it, once you've got a good calculator, this stuff gets, okay, next. So we'll get there. Now, this is a chapter on, if you were to write a book on how to do something, how did he write the resistive book? Okay, he wrote it, Resistive Circuits. So here's voltage, here's current, here's resistance, and then how would you handle the next part of it? If you had everything in series, right? If you have a bunch of series resistors, how would you handle it, right? And then you would say in parallel. And then what's the next chapter? Series parallel. And then what? Then your theorems, your Thevenin and Norton. And then mesh, node, and mesh. And you're pretty much done. Okay? Now, what do you think this book is organized as? Here's your inductor and your, excuse me, and your capacitor. Series RLC circuits, parallel RLC circuits, series. You follow me? Thevenin and Norton RLC circuits, node and mesh RLC circuits. So what are we studying today? Series impedance. All right, you get the picture? It's the same stuff. It's just it's piling on. Yes, it is. Now we're dealing with imaginary numbers. That's the only difference. The only difference. Okay. So here I have a resistor and a capacitor, and I also have a frequency. Okay. So now the x sub c is equal to minus j over 2 pi fc. X sub l is j 2 pi fl. You tuck those away, write them on your shoe, put them on your piece of paper as you have to remember these, and then you go forward, okay? Please use these as something that you do not forget. What is J? Well, in your calculator, J is equal to I. Why do we not use I? Because I stands for current. In electrical circuit books, I is always current. So we use J as a square root of minus 1, the imaginary number. You say, you're using imaginary numbers? How can they be real? Well, because they don't provide real power. They provide resistance to the circuit, but they don't provide real power. They're storage devices, but they don't chew up power. That's what they're about. And why are we concerned? Because even though we work most of our problems in single phase, most of the actual problems that you will see in the real world are three-phase problems. We work them single phase because we want you to understand the circuit without confusing you with all this other stuff over here about three-phase. But most of the problems having to do with what you actually deal with in this sort of thing are three-phase problems. So let's just go ahead and see what this problem is. So right now, see what they've done is they've said, okay, can everybody see that, or do I need to expand it a little bit? Is that better? So here is the calculation for x sub c. Here is the actual device. So instead of writing 910 picofarads, you write minus j 11.66 k ohms. And it's in ohms. So the units of resistance are what we call impedance now. Instead of what we call x is impedance, R is resistance. So if you have an x sub L, it is inductive impedance. If you have an x sub C, it is a capacitive impedance. But we don't really care, we say impedance. Okay? So instead of, what's the total resistance of this puppy right here? So you start here, you go through a 47K, and then you go through another one. We just use the capacitor, but we don't write 910 picofarads. We write what? Minus j 11.66 k ohms. Now, what's the resistance, or what is the total? The R plus jx is equal to z. So the real plus the imaginary is called the impedance. Now, what is the impedance? We write it as z. Okay, so what is the z instead of the R of this whole thing? Now the fun starts. Get your calculator out. Put it in what mode? Complex mode, which is the second one over. Everybody got their calculator? If you don't have a calculator like this, it doesn't have to be this one, but like this, get one. Please. If you can't afford one, I'll buy you one. This will save you getting this through this course. Okay? $20. I saved you on the kit. I saved you on a book. But I'm asking you, pleading with you to get a calculator that does this kind of calculations, okay? And I gave you the numbers for it before, but I'm going to go through the steps today. So what do? So you say equals. Okay, now you're ready. So you say 47, and you can drop off the K, all right? Minus what? 11.66I. So you now say what? Z is equal to 47, and you can drop off the K, minus 11.66I equals, all right, I get a number. Then I do a option down, 1 equals, okay? What's your final answer? 48.42 K at angle minus 13.93 degrees. Everybody should get that. If you don't get that, I want the answer in polar. All right, practice that until you can get it. Anybody have any questions about that? Now, I could go back and look at each of your calculators and say, now, did you get that? Did you get that? Did you get that? Did you get that? I'm going to trust you, you got that, okay? We're going to go through today basically just very slow, but you now have a real fair warning that you need to be able to get this calculator or calculator like this in order to get this to work, okay? Does everybody see does everybody see how easily you got that? Using that calculator? And how hard it would be using any other calculator or a slide rule? Slide rules, you had to basically go back to sines and cosines. You had to do all this stuff. Find the angle. Find the angle. You had to do all that by your step by step by step. With this thing, it just plops out. You say, are you being cheated? This is one of the times when I don't think you're being cheated. I mean, I had to do the slide rule. I'm old. I appreciate this calculator. And the other reason I appreciate this calculator is because this calculator can be used in all the PE tests that you ever want to do. If you want to take the fundamentals test, you got the calculator that'll work for it. If you want to do the professional engineering test, you got the calculator to work for it. So you're being prepared if you want to take the PE test, the fundamentals test, and also to get through this course effectively. And it works, and it's 20 bucks around. Anybody buy one for lately? How much? Huh? $20? Okay. Does anybody have to spend more than that? Okay, so you got one and it's about 20 bucks, right? If you haven't gone out and gotten one yet, now hopefully you will see the need for getting a calculator like this that busts these apart very quickly and gets the answer right away. If you don't see that, you will, or you'll suffer. How's that? So his approach, my approach, knock it in the head with this thing, and you can look through and see what he says and how he says it, and that's the old approach to doing it. But daggone it, this works, and it works so well. You can go back and forth with stuff. I'll get off my soapbox. That's my soapbox item for the day is please think about getting this calculator, and then we keep going. Okay, so now we're going to do another one. What is this? Oh my goodness. Now we've got what? a resistor, an inductor, and a capacitor. Now we got some plus J and we got some minus J. Okay, this is the minus J, this is the plus J. Now, the good news about this is that usually in test questions, I don't give you a frequency. I just write the X sub C or the X sub L. In other words, I take this step and do it for you. Sometimes I don't. Sometimes you have to calculate that, the resistance and the resistance. Sometimes you don't. I'll just write the X sub C, the X sub L, and away you go. I don't even tell you the frequency. You don't need the frequency. You just need to know the X sub L, X sub C. So there's a frequency involved, but we don't even give you that frequency because we don't care. But, you know, we'll write a capacitor and give you an X sub C. X sub C equals blah, blah, blah. So many J. It's a minus so many J. And we'll write an inductor, and we'll write an X sub L. And it's so many X sub, it's J. This is a minus J number. This is a plus J number. Okay, that's all it is. Okay, but here, they do that. They do the calculations for you. So the X sub L is equal to what? X sub L, in this case, is equal to 2 pi FL. They give you the frequency. They give you the millihenry, and it is J1885 ohms. So it's J188.5 ohms. Now notice again, that's in ohms, but there's a J in front of it, okay? The implication there is it's an imaginary resistance, which is not to say that you can't actually see the effects of this. You can see the effects of it. The only reason it's imaginary is because it is on, this is the real axis, this is the plus J axis, this is the minus J axis. It's someplace up here, okay? But it's real in the sense of it has an effect on your circuit. It is not imaginary in the sense that you can't see it and it never does anything for you or whatever. The word imaginary in this case is not the same as when you think of something that you can't see or feel or whatever. You can't ignore it. It's there. It can bite you. Okay, so now, does everybody follow that? It's only, the reason we call it imaginary is because we're sticking it on the y-axis. It's real in the sense that it affects your circuit. It's imaginary in the sense that it goes up or down the y-axis. So the resistance in this, in many cases, is something like this, or something like this. Okay, so what is our X sub C? Minus J over 2 pi F C. So what is C? 270 nanofarads. What is nano? 9. Pico is 12, nano is 9, micro is 6, milli is 3. Those are the only ones you have to remember. Pico, I don't know how you remember pico. Little, nano, 9, micro, 6, minus 6. Okay? Milli, minus 3. So it is 270 nanofarads for the X sub C. So the X sub C is minus J 294.7. All right, so the resistance in series is what? 500 plus J, what? 188.5 minus J 294.7. And the units of all these are ohms. Now, what is the total Z? Used to be the total R. Now, what is the total Z? Total Z is what? Punch calculator? Pretty easy, isn't it? It's what? Menu equals complex, you got to set it in complex mode. Okay, that's the key. Once you've done that, the rest of it's pretty straightforward. 500 plus 188.5 I minus 294.7 I equals. Okay, option, excuse me, Down arrow, 1, answer is what? What is your answer? Z is equal to what? 511.1 at minus 11 point some degrees, 0.99 degrees. Now, do you say, does this J take away from this J? And the answer is obviously yes, because this one goes up, this one goes down. Which one goes bigger? Who's the big boy? This one. There's more here than there is here, right? So you go up 188, you go down 294. What would be the net of those two? Well, minus 108, right? Or 106 point something. Everybody follow that? So you go up with the L, you go down with the C, and the net is still down a little bit. Now, how else can you tell if you got the right answer? Kind of. Is this more of a capacitive circuit or an inductive circuit? Is this a bigger, if this is a minus sign, okay. Right now. Okay, so let's just keep going. Does everybody follow that? Did everybody get that? Practice, practice, and practice, and practice. Make sure you get that. Okay. And notice what he does. He goes through this and, blasts away and blasts away and blasts away, and he comes up with the same number that. Now, and then he goes through another frequency. Okay, so he does it. There's the number right there, and we got it in about how long did it take us to get it? He rounded it, but how long did it take us to get that? 10 seconds? Maybe? Not hard, right? No. So that's how that's done. Okay? And he does another frequency, and away we go. Okay, so here's what he just did that I just did. Okay, so you go up, you go down, blah, 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 and all that kind of stuff, and there's your final Z. And another example. Oh my goodness, he's giving us all kinds of examples. Okay, input is 1. So here, what did he do? He did what I said that you usually do. We wiped out the 1 over 2 pi and the 2 pi f and all that kind of stuff, and we just give you the number of the impedance. So we take out that first step. We just say, you can do this. We can get to this point. Now, why do we do that? Why don't we make you go through that first step? Because if you miss the first step, the rest of it's messed up. So if we ask you, the primary objective of this is to get you to figure out how to do this. So if you mess up at the prior step and you get the wrong number, you've messed the whole thing up. So we take that away from you so that, you follow me? You just have to crank through this part of it. All right, so how would you do this? Easy. Series, plus, right? You add them together. What do you do? How do you do this one? Menu equals the 750 plus 600i minus 200i equals 750 plus 400i, okay? Option, down arrow, 1. Answer in rectangular, 850. So the answer to this one is what? 850 at 28.072 degrees. Did everybody get that? All right.
You're done with chapter 2.
Once you mastered that with a calculator, there's nothing in chapter 2 that we're going to tell you that's going to make any difference. The techniques employed for series AC are the same as those for DC. Period. Okay? Now what do we ask you to do? B and I. You knew there was more, right? So how would you find the voltage across the capacitor, the voltage across the resistor in a circuit like this? Well, you would do it the exact same way you did it in resistor circuits. The 1 is the value of the voltage. Now, is this peak or RMS? Peak. So your answers will all be in peak for this problem. If I said instead of writing it like that, if I just wrote it like this, 1 volt, that's assumed as RMS. But if I write it like this, 1 sine 2p, blah, 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 all that kind of 2 times pi, 1000 t, this is assumed as peak. Because that's what it is. Does everybody understand the difference? It's subtle, but it's real. Most of the time, we write it like this. And sometimes even put a plus like it. It makes it look exactly like DC. But you assume then that is RMS, unless they tell you 1 volt peak. Or they could write it 1 volt peak, like that. Or they can write it 1 peak, peak with a little p, that means peak. Or they can write it with 1 RMS, or 1 volt RMS, and that means RMS. But if they don't tell you, it's this. But here it's peak, but we don't really care, so we're working the problem, and peak doesn't matter. So what would be the value of I? Okay, so now we're down to having to calculate all this stuff and then find, like we did before, I equals V over, it used to be R, now it's Z. This is our Z, this is our total impedance or resistance of the whole circuit, right? So how do you do that? Well, it's a two-step operation. First of all, you've got to calculate these resistances. You've got to calculate what the resistance is of this, which is 2.2K. What is the resistance of this? Well, it's 1 minus 1 over 2 pi F. What is F? 1,000 times the C. And you got to calculate that. And that's what they do. The very first thing they do is they calculate the value of X sub C, which is that right there, okay? So they calculate the value of X sub C. So basically, this circuit is like this. It's 1 volt peak. And then up here, you've got a resistance, and over here, you've got a capacitance. But I'm going to write it, instead of 33 nanofarads, I'm going to write minus J 4823, which is exactly what it is. And up here, it's 2.2, Ted, 2.2K. By the way, we usually make these numbers, we usually make this so that these numbers and these numbers are about the same. If they don't, one dominates the other, and you don't have a real circuit. But basically, if these are kind of close, your numbers are kind of unpredictable. So basically, we usually make the problems so that this number and this number kind of close, all right? So that's our X sub C. So immediately I now say, what would be my I? And he writes it little I. I should write it little I. Why do we write it little I? Little I signifies it's an AC variable as opposed to a DC variable. So basically, I is equal to V1 over Z, which is what? 2200 minus J 4820. 23. And you write it just exactly like that, okay? Now, that's my term for I, and that goes right into calculator exactly like that. And how do you find it? You don't have to go through a lot of steps. Let's do it with a calculator and find that number. Okay, it's 1 divided by, use your parentheses, 2200 minus 4823i, end parenthesis, equals. Option down, 1 equals. What is that? 0.000188 at angle 65.48. Did everybody get that? Yes, sir. Use what? Well, this whole problem is worked with peak. So this would be a I peak. You don't have to write IP as opposed to IRMS. It's just this whole problem is worked with I peak because that's what they give you. You know, you work the whole problem based on what they give you. That's all it is, okay? That's good. Good question. All right, does everybody see this? It's 188 microamps at 65.5 degrees. He rounded, I didn't. It's 1886412. At some point you stop. You don't have to go six figures. You can go 3 or 4 and you're good. I just don't want you rounding them all to 1 figure. Please don't do that. If you rounded that to a 2.2 milliamps, and you carry that forward in the next step of a problem, your answers are going to be off significantly, and I have to grade these at some point. So get into the habit of at least carrying it through for 3 or 4 significant figures. Okay, sig figs, 3 or 4 figures. So there you go. Now, how do you find VR, VC? There you go. And that's it. Now, what would be the other way to do this? How do you want to find? I want to find the voltage across the 2.2K in one step. Used to have a program on TV about I can name that tune in 4 notes. And the guy would say, I can name that tune in 3 notes. And then somebody would say, I can name that tune in 2 notes. And then somebody would say, I can name that tune in 1 note. And every once in a while they would get it. Most of the time they would not. But anyway, how can I do that? Okay, I want in one step to find the voltage across the 2.2K. How would you do that? It's voltage divider, right? Can you use voltage divider? How many of you think you can use voltage divider? If you're awake. No. Yeah. It's cold, I know. But you can use all the rules and all the things you did before, you can still use. And you can use it. So you can use that here. Now, he did it one way, I'm going to do it the other. So let's just do this. It's 2.2 over, okay, so it's 1 times 2.2 or over 2.2 minus J for 823. All right. Now, well, that's the voltage divider, right? It's the resistance that you have over the sum of the resistances, and the sum of the resistances is this. And I put it in k ohms, but you can keep it as is. Now I want you to solve this on your calculator. Can you do this on your calculator? Yes. You can say 1 times 2.2 divided by parenthesis 2.2 minus 4.823I in parenthesis equals, what's your answer? What did he get for an answer? Everybody see that? How would you do voltage divider for the capacitor? What's the capacitor voltage? And you say, you mean you can stick a voltmeter across the capacitor and measure that voltage? Yes, that's exactly what it means. Except for the fact that the voltmeter reads in what? Other than that, you're in. Okay? Follow me? That's it. So now I'm gonna go for the capacitor voltage. How will you write that? Somebody tell me, how would you write the capacitor voltage?
Be negative 4.823 divided by the 2.2 minus the 4.823.
Yeah, that's an 8.23. Minus J 4.823 divided by 2.2 minus J 4.823. And that would give me my capacitor voltage. Okay, let's just try that and see if we can figure that out. If you can read my writing, you're better off than most. It's 4.823 or 2.2 minus J 4.823, the whole thing times 1. 1, okay, mu equals 1 times, now you use the minus key up here. You don't use the, when you're subtracting, you use the 1 down below. When you say minus J blah blah blah, you use the minus key up above. Does everybody follow that? Minus 4.823I divided by parenthesis 2.2. Now you use the minus key down below. Minus 4.823I in parenthesis equals option down 1. And the answer is 0.909 at angle minus 24.51. Now you're going to ask me how I can get 1 is equal to you're going to ask me how 1 is equal to 0.9 plus 0.4. How can you answer that question? It is not done. Here's my voltages. Okay, so here is my voltage. Here's my total voltage. It's 1 volt, or it's 1 volt. Everybody agree with that? It is the sum of these two arrows, this one plus this one. All right? That's it. So things that can use to not make not any sense at all, how can you say 1 is equal to this plus this if you're just taking into account magnitudes. You can't anymore. It's a magnitude and a direction. So this phasor and this phasor add up to this phasor. Okay? So you jumped off of just this number line, and now you're using two-dimensional numbers to explain everything. And how can you do that? Because this is AC, and this is the steady state circumstances. This is not the transient when you turn on a switch. This is just the steady state circumstances. So that's all you're doing. But it's enough to effectively give you the ability to calculate any AC circuit that you want. Does this work with other waveforms? The answer is no. This is a sinusoidal waveform only method for doing things. But by the mere fact that most things are done using sinusoidal waveforms, it works for a lot of it. It works at explaining a lot of what we are actually seeing in the real world, okay? Now, this would be, if you looked at these on the wave, on an oscilloscope, what you would actually see. You would see three waveforms. The blue is your input waveform. Your green is your resistive waveform, and your C is your capacitive waveform. Okay, does that make sense? That's exactly what it is. They're time shifts, and they're measurable. All right, and that's if you did it in a simulation, and you can do these simulations on multisim. Multisim is on the computers in the laboratory. I do not go through multisim in this course very much at all. It's not because I don't believe that multisim is useful. Basically it's a problem-solving course, and we do the problems here, and if you want to check them, that's one way of checking them. But very rarely do I actually ask you to do that. Okay, so this is another one. Current one. Oh, now you're really getting nasty because you're putting current in here. It's the same stuff exactly that we did before, right? Here is one with what? Two voltage sources. Oh my goodness. So how would you do this one? By the way, with two voltage sources, what do you have to do? They have to be at the same frequency and the same, they can't, you can't introduce two frequencies. So when you do something like this with AC, these two have to have the same frequency. They have to, or it won't work. All right, that's superposition. Or you can work the problem how? It's this one minus this one, because you're just going around a loop. Find the current. This voltage minus this voltage times whatever, and you're done. Can you put a plus and a minus on voltage supplies? Yes, you can. And you actively look at them exactly the same way you do DC, even though they're AC, and even though they're constantly changing. You basically say, okay, this one is a plus, this one is a plus, this one and this one, they fight each other. This one and this one fight each other. So if you have a waveform that is doing this, and then you do another one that's doing this, but it's over here, when you're going around the loop, it's minus this one plus this one, or this one minus this one, doesn't really matter. But they're fighting each other. So the difference between here and here is this one minus this one. Just like it was in DC. Okay, enough on that. He talks about speakers, and woofers and kind of interesting stuff. I'm gonna let that go. It's nice to have stuff like that in there, just to give you a little bit more of a examples of stuff that you can use it for. But like I said, I'm not into that part of it, so I guess I could just kind of let it go. Practical inductors. Practical inductors do not have just resistance or just impedance. They have a resistance as well. So every inductor has this and this. And their quality is a relative term based on the Q. So it's the X sub L over the R coil. So a high Q, high quality inductor is one that has a lot of inductance for a little resistance. Okay? Again, you don't care other than the fact that Q stands for quality. And a real live inductor has both of these. So you can flat out measure a inductor, and you can measure for resistance. You can put it across an ohm meter and measure for resistance, but then you have to put it on an induction testing machine to test it for its L value. In other words, if you don't know when you pick up an inductor and you don't know what it is, you can't put an ohm meter across it and test it. You can test and get this value, but you can't find this value. In the back of 2380, there is a machine back there that you turn it on and it'll give you this and this value. All right? It's been there for a long time. It was there when I came, and I've been here for 40 years. So it's old, but it works. Slap it on, turn it on. I want to know the L, I want to know the C, it'll tell you. And you'll have to do that in the labs. Okay, so there are some questions in this chapter. Let me see what I asked for. I'm not sure right now. Chapter number 2, 1 through 12, 24, 28, 32, 33, 36, or excuse me, 33, 43 through 46. Wow, that's a potload. You know, that's going to take you a while to get through those, but that's it. I mean, you can work these, they're not hard, and it's good practice to do these. Let me just look at a few of these, because I have done these. I haven't done them for a little while, but I have done them. Let's go through and look at a few of them. 1 through 12. These are the same that we just did. Okay, 1 through 12. Now here, in 12, it's just a capacitor. So let's look at that one for a minute, because that is kind of a different one, and we'll be done here in a minute. Okay, so number 12, we've got a voltage supply, voltage, and then we've got 1 volt peak, and then we've got just a capacitor, nothing else. So it's minus J X sub C. If our voltage is that, what is our current? I is equal to V1 divided by R, or Z, which is minus J x of C. All right, so when we say a minus J in the denominator becomes a what in the numerator? Does everybody agree with that? A minus J in the denominator becomes a plus J in the numerator? Excuse me. Yeah, that's exactly right. So what happens to, okay, so if this is my voltage, my current is like this. It's 90 degrees ahead of the voltage. Here's my voltage, here's my current. Because that J says move it ahead by 90 degrees. So that's number 12, okay? So draw the voltage and current waveforms for the circuit, blah, 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 with a peak of blah, 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 okay? And that. So there it is. In a purely capacitive circuit, it's ice, okay? Current leads voltage, and in purely capacitive by 90 degrees. And there it is, 90 degrees. That's the J. The J moves it 90 degrees ahead. If it was an inductive circuit, it would move it Eli. In an inductive circuit, if that was an inductor, it would be like this. Here's my voltage, here's my current. Voltage leads current in an inductive circuit. If it's a pure inductor. It never is. But in a capacitive circuit, current leads voltage. In an inductive circuit, voltage leads current. It's like the dog track. Who's ahead? Dog 1 or dog 2? All right? Who's leading in this case? Current is by 90 degrees. He's way out ahead. And this one, who's ahead? Voltage by 90 degrees. He's way out ahead. That's it. And then there's some more. We'll work on these. We'll come back and do this, finish this off. We'll work some of these problems. I'm not going to just let you leave you high and dry on these, but I'm not going to work them all. I'm going to work some of them. But I want you to practice these. And there are answers to some of them in the back of the book. And there's a bunch of, there's just a bunch, but they're quick. And you can do these. I'll send you a quiz. I don't know what the quiz is going to be on. Probably something along these lines, but I'm not really sure. It could be something on chapter 1, chapter 2. But we'll send you something in the mail. You'll get that, have to hand that back in on Tuesday, and you'll do these problems, get these problems done. And we're preparing you for a test, okay? The test will be basically like your DC circuits test based on now capacitors, inductors, all the rest. And that's what you're going to have. It'll be before the midterm, or it'll be before spring break, before the first week in March. But we're getting you ready for that. If you want to know where we're at, what we're doing, we're getting you ready for a test on V equals IR, but it's now with capacitors and inductors. Okay? All right. Any questions anybody's got? We'll get you through this. They're not hard. Is anybody just so taxed that they can't figure any of this stuff out? Oh, pretty straightforward. It is straightforward. It's just like resistive circuits. If you got through resistive circuits, you should be able to get through this one. And it looks strange, but you say, how can this possibly be? You probably ask the question a lot of times, well, he's talking about imaginary stuff, but he's saying it's like it's real. It is. It's real. It explains how currents react in capacitors and inductors as well as resistors. Okay? It acts differently. That's all this is. I'll see you in lab.